Okay, we're going to start with chapter 11. It's the first chapter that we're going to talk about, and it's going to be on test 3. And it's sort of a continuation of chapter 10. We're still talking about fractions and rational expressions. This chapter, in my opinion, is going to be a little bit more manageable though, because unlike chapter 10, in chapter 11 we get rid of the fractions. There's no longer this denominator that's sort of that we have to string along throughout our problem. So it's not really a new idea. It's one that you should have picked up in intro algebra. We're just applying it to a different sort of equation. So here's something that you've sort of seen from intro algebra. I'm just going to write down an equation, a simple one. For instance, say we had x over 4 plus 3 over 2 equals, I don't know, let's say 5. Well, one of the guidelines that you were given in intro when you were faced with an equation with fractions was to find a common denominator between all of the fractions included in the equation, and to take the entire equation and instead of rewriting every fraction with a common denominator, what we did was take that common denominator and multiply it by each term in the equation. And so it would look like this. If our equation was x plus 4 plus 3 halves equals 5, the common denominator between 4 and 2, well, would actually be 4. 8 would work, but we'll use the smallest, the lowest common denominator, 4. And what happens? Well, 4, by multiplying by 4 on each side, is simply going to knock out the fractions. So on the left, and I already have a 4 over here, so I don't really need that arrow. On the left, 4 times an x over 4 would look like this. 4 times 3 over 2 would look like this. And now on the right there is no denominator, so it's just 5 times 4 gives us 20. Now basically what we have now is a 4 in the numerator of each fraction, and we picked 4 based off of the fact that the denominator would divide into it. And so what we see here for the first fraction, the 4's cancel, leaving us with just an x. 2 divides into 4 and gives us 2, and the 2 in the denominator cancels out. And once we've done that, there's no more fractions. At this point we just simply have a x plus 6 equals 20. A little bit more manageable. And so that's the idea behind chapter 11. It's just the only difference is that these denominators are not just simply going to be numbers, they're going to be polynomials. Okay, but the idea is the same. We multiply the equation by the lowest common denominator. We don't change all of the fractions. We don't keep or drag along the denominator with us throughout the entire problem. Okay, so here are some guidelines to follow, 1 through 5, for handling equations with fractions. Okay, I encourage you to read through that, but here in a minute you'll see me work some problems, and these of course should make more sense. Something new down at the bottom of the page that you may have not ran into yet are these extraneous solutions. Okay, In a previous chapter, we looked at the domain of rational expressions, and we decided that based on the denominator there were certain values that x could not be, or else we ended up with a 0 in the equation. So suppose that we had this equation, 1 over x plus I don't know, 2 over x plus 2 equals 3. Alright, now I'm not actually going to work this out. I'm just going to say, suppose that we got to the end of working this particular equation out, and we come up with x equals -2, for instance. Well, if you take this supposed solution back to the original equation, what happens is this -2 makes this denominator, if you plug in -2 for x, this denominator then becomes equal to 0, and 2 divided by 0 is undefined. So this is not a solution in the usual sense. We call this extraneous solution. So in this chapter it becomes somewhat important to check your answers at the end. Now there's another type of equation where you can run into extraneous solutions other than ones that contain fractions. Those are equations that contain radicals, and such as the square root, but we're going to talk about those in a later chapter. We're just going to focus on equations with fractions in chapter 11. Okay, the next page we're given two methods on how to handle equations with fractions, specifically one's fractions with denominators that are polynomials with a variable. Okay, so here's our initial equation, and what we do is we pick out lowest common denominator. Well, we need one of each factor that appears in the denominator. So lowest common denominator would just be the denominator of one times the denominator of the other, since they're just completely different. And method one is pretty much what we did with the first equation that I showed you when we started this chapter. We've taken the original equation, which this and then the 0, that was all a part of the original equation. If you look back up here by the star, we had this and we had 0, and that's all. Well, this first method that we show you is where we simply take the lowest common denominator and we multiply it by both sides of the equation. Okay, and so you can follow along in the workbook and see how that works out. I am going to skip ahead to the next page where we talk about method 2. Alright, before we get to method 2, we see that we're reminded of cross multiplying when we run into a particular type of equation. This is a proportion. Should ring a bell if you happen to go through intro. It's where we have one fraction on one side of the equation and another fraction on the other. So fraction equals fraction, And the important detail that's easy to overlook here is that there's one fraction on the left, one fraction on the right, and that's it. Okay. So for instance, if we were to have an equation like this, this would be a proportion. Okay, this is x here. This would be a proportion. X and 2, they're all wrapped up inside one fraction, and then 3/4 is a single fraction on the right. Now, I can easily turn this into an equation that is no longer a proportion by adding an extra term on one side or the other. So I can just simply go off to the side and add a number to it. This is no longer a proportion. And therefore, to solve this equation, we cannot cross multiply. This only applies to proportions. Alright. So, example 2 wants us to consider two ways to approach solving a proportion. Okay. First one is to cross multiply. We simply take the denominator of one side and multiply it by the numerator of the opposite side. Both ways. We end up with an AD and a BC. Alright. Now, what if we go about it a different way? What if we apply what we did in the previous method, where we take the lowest common denominator, which in this case would be B and D, and we multiply it on both sides. Okay, the left side becomes A, B, D over B. The right side becomes C, B, D over D. If we simplify both sides, we see that B and on the left cancels and D on the right cancels, and we end up with AD equals CB, which is identical, disregarding order, to the result that we got over here by simply cross multiplying. We have AD, or A times a D on the left, and a B times a C on the right. Same thing. So either way is a totally legitimate way to go about solving these types of equations. Equations that only involve two fractions or two rational expressions. So we see that in the next starred comment, method 2. You can see that we have the fractions on opposite sides of the equation, and we simply cross multiply. 3 times x plus 3 ends up on the left, and 1 times x minus 5 ends up on the right. Okay, and at that point we no longer have fractions, and so we revert back to what we simply did in intro algebra. We get the x by itself, and obviously there is no x squared term, so we can go about solving the equation by just isolating the x. Okay, so we have two methods. Which one that you want to follow is up to you. So example 3, I guess what we could do is to say if the fractions are on the same side, then maybe we should go with the least common denominator method. Alright, we just simply take the original equation, and we take the least common denominator and multiply it by both sides. Okay, so what is the least common denominator? In this case it's real simple. Neither of the denominators in this case are factorable. So what we end up doing is just simply multiplying both sides of the equation by an x plus 4 and an x minus 1. What does it look like when we do that? Well, we have to take all of this and basically put it on the top of each fraction over here on the left side of the equation. Right side's simple. We apply the zero property of multiplication, which just tells us that if we multiply a bunch of things together and 0 is a part of that product, then that just works out to be 0. Now, back over on the left, we write 3 x plus 4 x minus 1. Then we write minus 2 x plus 4 x minus 1. Lowest common denominator goes on top of each fraction. On the bottom of the first one we have an x plus 4, on the other an x minus 1, and we'll go ahead and write out the right side of our equation, which is just 0. Now for this fraction, x plus 4 cancels. For the second one, x minus 1 cancels, and now we have 3x minus 1 minus 2 times x plus 4 equals 0. No more fractions. Okay, the equation becomes a lot more manageable. So to finish out this equation and solve for x, we would now get rid of parentheses. 3x minus 3 negative 2x minus 8 equals 0. We combine like terms now. We have a 3 and a minus 2x, which gives us 1x, and then we have a negative 3 and a negative 8 to give us a minus 11. And now we simply add 11 to both sides and we get our answer, x equals 11. Now the only thing that we really need to check in this case is to go back up here and check out the denominators. Will 11 make x minus 1 0, or will 11 make x plus 4 0? And the answer to both of those questions is no. So this is a bona fide solution. It's not an extraneous solution. Okay, example 4. You see that we have a fraction on the left, fraction on the right of the equal sign. So what we'll do to start out solving this equation is to just cross multiply. We have an x times the x plus 1 that is going over to the left, and we have a 2 times the x plus 3 on the right, and forms a little heart just to show that we love algebra. And now at this point we distribute to get rid of the parentheses. Fractions are gone. We get x squared plus x equals 2x plus 6. We see the x squared term. Okay. At this point you fall back on what you learned in a previous chapter. This is a quadratic equation. You want to get it in standard form, which is to say you want to move all of the terms to the left or the right. One side or the other doesn't matter, but you want 0 on the other side. So my x squared term is on the left and it's positive, so I'm going to keep it where it's at and move the 2x to the left, and I'm going to move the 6 also, so I'm going to write minus 6 below both sides of the equation. Now These terms on the right cancel, so they leave us with 0. And on the left we have an x squared minus x minus 6. Okay, and we factor x minus 3, x plus 2. This factor is going to give us an x equals 3. This one will result in an x equals negative 2. Do either one of these numbers make the original denominator 0? The answer to that is no. So these are not extraneous solutions, these are just solutions to the original equation. Example 5, we cross multiply. 2 times x minus 2 equals 3 times x minus 2. Alright, now we distribute. We get a 2x minus a 4, and we get a 3x minus a 6, just to get rid of the parentheses. Now we move our terms around. We do not have an x squared term, so we simply just want to isolate the x. So I'll start out by combining the x's from each side. Subtract 2x. We end up with a negative 4 equals x minus 6. We add 6 to both sides, leaving the x by itself on the right. And we get x is equal to 2. Now, the check for these equations is to take the number, go back to the original equation, and see if that particular number makes these denominators equal to 0. And if you plug in 2 in the place of x and subtract 2 from it, you get a 0. And so this solution is causing the original equation to have a 0 in the denominator. This x equals 2 is what we call an extraneous solution. Alright, example 6. We have both fractions on the same side of the equation, and I'm going to show you that we can easily convert this type of equation back to the ones like to type in example 5. So if you like to cross multiply, this is what you'd want to do. Keep the 2 over x plus 2 on the left. Move this fraction to the right side, x over x plus 2. But since we moved it, we need to put a negative sign in front of it when it sits on the right. But now we have the equation set up to where we can cross multiply. We couldn't do that with the original form of the equation. So one fraction on the left, the other fraction on the right, we cross multiply, and we get 2 times 2x plus 2, and then we get a minus x times an x plus 2 on the left or the right. We distribute to get rid of our parentheses. We get a 2x plus a 4, we get a minus x squared, and we get a 2x. Alright, when we try to combine our x variables, just our x terms, not the x squared, we subtract 2x from both sides, and we see that those terms knock each other out, and we're left with a 4 equals minus x squared. Okay, so we have this x squared term. We need to put it in standard form. I am going to move the x squared to the left, and we get this for an equation. X squared plus 4 equals 0. and you should recognize this polynomial as the sum of two perfect squares. This has no real solution. And so we just throw up our hands and say no real solution. That's as far as we can go with this equation. So this next page is simply showing us a different type of equation. It has fractions. Main difference is, if you'll take a look at this start equation, is that there are now 1, 2, 3 fractions. Okay, there's no longer just 2, so we can't write one on the right with the other on the left and cross multiply. That sort of goes out the window when you have more than 2 fractions in an equation. So what they do is they just simply walk us through one that has 3, and you see that we don't use the cross multiply method, but we do multiply the entire equation by the lowest common denominator. And so that's what you see here, here, and then on the right side. You should just see that we have lowest common denominator times the first fraction plus lowest common denominator times the second fraction, and then on the right side of the equation, lowest common denominator times the third fraction. Alright, and it's really not too bad to write this part out. It's quite a bit, but we've used the lowest common denominator factored form, and so what you see is that the idea is still the same. The fractions cancel. Okay, first fraction times the LCD denominator completely cancels out. The LCD times x plus 1, the x plus 1 cancels, and so we're left with the 3 times the x minus 1. Okay, LCD didn't completely cancel out this time, but the fraction is still gone. And then on the right side of the equation, the x minus 1 cancels, leaving us with an extra factor in the numerator of x plus 1 times the 2. Okay, but the idea is still the same. We multiply the entire equation by the LCD, and that gets rid of all of the fractions. So let's try to work a few on our own. Example 7. In this case, there's only numbers in the denominator, so the question is, what is the LCD of 5, 3, and 6? That would be 30. But we're not going to change each denominator to a 30. What we're going to do is take each of the fractions in the original equation and multiply it by 30. Alright, and so it ends up looking like this: 30, 30, 30. Now we go back and we look at each denominator and simply divide it into the least common denominator. Divide. Take the 3, divide it into the 30. Take the 6 and divide that into the 30. And so the whole point of multiplying everything by is to knock out the denominator. 5 goes into 30 6 times, and we do not have to write the 5 down now. It was absorbed into the 30 and gave us the 6. 30 divided by 3 is a 10. So now in front of the x plus 1 on the top, we just have a 10. And then 30 divided by 6 is a 5. So we drop the 6, put a 5 in front of the x plus 1, and we're done. There's no more fractions. At this point, we do have to go back and distribute, but this is something that you probably have gotten a lot of practice with if you took intro. So this part would end up being a 6x minus 12. The next one, negative 10x minus 10. And on the right side of the equation, a 5x plus a 5. We go through and combine like terms where we can. On the left side of the equation, we have a 6 and a minus 10x. That gives us a minus 4x. We have a negative 12 and a negative 10. That gives us a minus 22. And we just copy down the right side of the equation. And now we're going to move the smaller x, the minus 4, over here to join the 5x, and that will give us minus 22 equals 9x plus 5. So to finish out this problem, the x is on the right side and we just need to get rid of the 9 and the 5. So we subtract 5 first, we get a negative 27. We divide by 9 and we get a negative 3 equals x. Okay, we take our solution, and the main thing is you want to check and make sure that this negative 3 doesn't make any of the denominators 0, and in this case it can't, because there's no x variable in the denominator. However, if you do want to check and make sure you did the right work, just simply go back and take the original equation and replace the x with the negative 3. So we get a negative 3 minus 2 over 5, a negative 3 plus 1 over 3, and on the right side a negative 3 plus 1 over 6. Okay, this becomes a negative 5 over a 5 for this first fraction. A negative 3 plus a 1 becomes a negative 2 over 3. And on the right side we get a negative 3 plus a 1, a negative 2 over a 6. Alright, here we have a minus minus situation. Negative 5 over 5 is just a negative 1, and so this becomes plus 2/3, and a negative 1 plus a 2/3 would be a negative 1/3. And if you look on the right side, 2 over 6 will simplify to 1/3, and it was also negative. So in the end we have matching numbers on the left and right side of our equation. Therefore, our solution of x equals negative 3 checks out. Example 8, we simply take each fraction and we rewrite it with the lowest common denominator on the top of each one. Alright, also the lowest common denominator in this case works out to be just one denominator times the other one. We didn't have to factor either one of them, so we just take x plus 4 and x minus 2, put it on the top of each fraction like this, and then we also multiply it by, this isn't a fraction, but we still multiply it times the 1, x plus 4, x minus 2. Alright, we go back to our fractions and we cancel out the denominators. That was the whole point of going through and putting x plus 4 and x minus 2 in each term or each fraction, so that the denominators would cancel. So we want to go back and do that, and we end up with this equation. And I can put this x in the front or the back, but we have an x times an x minus 2. We have an x plus 4. 1 times x plus 4 is just x plus 4. And then on the right side we have an x plus 4 times a x minus 2. There was no denominator over here for the 1. We could put a 1 on the bottom, but point is, this does not cancel out either one of these factors, so we keep both of them. Alright, so we go back and we distribute. We want to get rid of the fractions, or the parentheses. We have to full the right hand side. And you see we have this x squared term, so we start trying to move all the terms to one side or the other. But when we subtract x squared from both sides, we see that they cancel each other out. Alright, so now we go about combining like terms, and negative 2 plus a 1 gives us a minus x plus 4 on the left, and we have a 2x minus 8 on the right. And so now we want to get the x's on the same side of the equation, so we add x to both sides, cancels on the left. We have a 4 on the left, and then a 2 plus a 1x on the right is 3x minus the 8. And now all we need to do is focus on getting the x by itself. Knock out the 3 and the 8. We start with the 8 first. That gives us 12 on the left and 3x on the right. We divide by 3, and we end up with x equals 4. We take our x equals 4 back to the original equation, and we check each denominator. So this denominator, x plus 4, if we replace the x with a 4, we get 4 plus 4 equals 8. The important thing is that that number is not 0. We check the other one, x minus 2 equals 4 minus 2. If we're checking our solution, x equals 4, we replace the x with a 4, we get 2 for that denominator, and so that is a good thing. It's not 0. So x equals 4 checks out. Example 9. Here we have two denominators, and this one, x minus 2, is not factorable. However, this one is. We can take out a 2, so it's real simple to factor it, but we can't overlook it, because now we see that this denominator is the same as the other one, except for this extra factor of 2. So instead of just simply multiplying the entire equation by x minus 2 and 2x minus 4, what we really need to factor by or multiply by is an x minus 2 and a 2. Alright, because this is equal to the lowest common denominator. So in this case, the first fraction ends up being x minus 3 times 2 times x minus 2 all over x minus 2. The second fraction is an x minus 1 times a 2 times an x minus 2. we just simply put the lowest common denominator in each fraction, and on the bottom 2x minus 4, which was already here, factors as a 2 times a x minus 2. So we can put either one, but I prefer to go ahead and just write it in factored form. And finally, on the right hand side, this also gets multiplied by the lowest common denominator. So we have times a 2 and times another x minus 2. Alright, go back to your fractions and cancel out the denominators. And for the first one, we are just left with 2 times x minus 3. For the second one, we have 2 times x minus 1. And for the right hand side, we can just put the number in front, and nothing cancels out, so we just sort of copy down everything again. Now the fractions are gone. That's the main point that you're supposed to take away from chapter 11, is how to take an equation with fractions and convert it to one that doesn't have fractions. Okay, over here on the right, we'll FOIL first, and then we'll multiply by the 2. So back on the left, we distribute the 2, we get a 2x minus 6 plus 2x minus 2. Here on the right, we'd have a x squared minus 4x plus 4. Over on the left, 2x and 2x make a 4x, a negative 6 and a negative 2 makes a negative 8. We distribute the 2 to each of the terms of this piece that we fold. So we get a 2x squared minus 8x plus 8. We have this x squared term that's not going to disappear, and so we want to move everything to this side on the right. So we have to subtract the 4x from each side to move it, and add the 8 to both sides. Everything on the left cancels, and we end up with 0 equals 2x squared minus 12x plus 16. Okay. I'm going to have to go back and make a little more room to work the rest of this problem out, because at this point, in order to solve our equation, we are going to have to use the AC method. So take this back up to the top. Well, actually no, we're not going to have to use the AC method, because this 2 that's sitting in front of the x squared term, well, actually we can factor that out using the greatest common factor. And so we end up with a trinomial with a leading coefficient of 1. A lot better to factor than the AC method. And it is going to break up into an x minus a 4 and an x minus a 2. Negative 4 times negative 2 is plus 8. And then you add the two numbers together to get the b, negative 6. And so at this point, we take each factor and set it equal to 0, and that will give us a 4, and it'll give us a 2. And one of these does not work. Okay, the 4 does work. If you take the 4 and plug it into x minus 2, 4 minus 2 is 2. If you plug it into 2x minus 4, you get 2 times 4 is 8, minus 4, 4. So 4 does not make either one of these denominators 0. So 4 checks out. On the other hand, if we take 2 and we plug it in, we get 2 minus 2 on the bottom, 2 minus 3 on the top, plus 2 minus 1 on the top, 2 times 2 minus 4 on the bottom, equals 2 minus 2. Alright, so these two denominators are the problem. On the top of each of these fractions, for the second one we get 1, the first one we get a negative 1, but both of them turn out to be 0. This 0 on the right is not the problem. It's okay. These zeros on the bottom of the fractions are problems, and so this result causes us to label this solution as extraneous. So example 10, you see that we have an x minus 2 and an x plus 2 for denominators, and these two denominators are prime. However, this first one is not prime, so you want to make sure that before you start trying to solve the problem, you factor that denominator. Now, you compare all three of your denominators, and you want to come up with the lowest common denominator. We have an x plus 2 and an x minus 2. Include one of each factor. And if you compare all three, you see that the most times that each one appears in any of the factors is 1 apiece. So we're just simply going to take each fraction and put our lowest common denominator in the numerator, okay. It multiplies each term, or just simply goes in the numerator of each fraction. We go back and we cancel out the parts that will cancel. So the whole purpose of this step is to get rid of the denominators of each fraction. Alright, now for this first one, x squared minus 4 is equal to both x plus 2 and x minus 2 multiplied. So this denominator cancels out both of those. And for the equation as a whole, we're left with 1 plus 3 times 2x plus 2, and on the right hand side a 2 times an x minus 2. We go back through the entire equation, getting rid of the parentheses, we distribute. We get a 3x and a plus 6, and on the right a 2x minus a 4. On the left, the 6 and the 1 combine to give us a 7. And at this point we subtract 2x from both sides, combine the x terms into 1. We get an x plus 7 equals a negative 4, and that results in a solution of x equals negative 11. Now the question is, does our solution actually check out with the original equation? So we take it and we replace all the x's in the original equation. Bottom of the first one, we have negative 11 squared minus 4. The second one, negative 11 minus 2. And the right side of the equation, negative 11 plus 2. Okay, this first one works out to be a 1 over a, let's see, 121 minus 4. This is the second fraction, ends up being a 3 over a negative 13. And then this one on the right hand side works out to be a negative 2, or a 2 over a negative 9. Alright, so back to the first one, we end up with a 1 over 117. We could transfer this negative to the 3 or make this a subtraction symbol. So we have 1 over 117 minus 3 over 13 equals negative 2 over 9, and I just simply move the negative to the 2 instead of keeping it with the denominator. Now these are kind of ugly fractions, so what I'll do is I'll just pull up my calculator and check to make sure the left hand side equals the right hand side. So our first fraction is 1 divided by 117. Then we subtract 3 divided by 13, and we get negative 0.222222, and so on. Okay, so what is negative 2 over 9 equal to? This is the right hand side. Negative 2 divided by 9 works out to be the same thing. Negative 0.22222 to infinity. So the two sides check out, and our solution of negative 11 is not extraneous. It is a full solution to the original equation. So last part of the chapter, we go back to something that we talked about earlier called literal equations, and now we're just going to revisit that, and we're going to look at equations that have variables in the fractions. Alright, now I'm just going to skip past the two examples on this page, but feel free to read them and study them yourself. It's just extra examples. I'm going to go down here and work the ones that we're given. Okay, so the goal is to get the particular variable by itself on one side of the equation, and here that particular variable is b. Okay, and now if we look at our equation, we see that b is trapped right here on the bottom of this fraction. We want to get that on one side by itself. First step at doing that is to just simply do what we've been doing. Okay, take the lowest common denominator, which in this case would simply be b times c. Okay, you just simply look at all of your denominators, b, c. The denominator of d, if you will, is 1. So LCD is BC, and what we've been doing up to this point is simply including it in each numerator or multiplying it by each term. So on the left hand side, our equation becomes BC times D. The first fraction on the right becomes 6BC over B, and then our last fraction becomes 5BC over C. Okay, go back to your fractions, cancel out what will, and in this case the B's cancel here and the C's cancel for the second fraction. Nothing cancels here for the left hand side of the equation, so we just simply write out BCD equals 6C plus 5B. We write everything down that didn't cancel out. So this is all that's left, but at least at this point we have no more fractions. Now it may look like we've went backwards because now we have the b in two different places, but we can collect all of the terms that have a b on one side, and the terms that don't, we'll leave them on the opposite side. So this 6c is going to stay there, we want to get this 5b over here to the left. Collect all of the terms that have the variable that we're interested in. So minus 5b minus 5b. The left becomes bcd minus 5b equals 6c. Now, do not try to combine these two terms. Yeah, they both have b's, but this one has some extra variables that the minus 5b doesn't. So these are not like terms. You cannot combine them. You just simply have to write bcd minus 5b. Okay, and that looks like a b there, but it's supposed to be a 5. Okay, that canceled. No, I'm sorry. That's supposed to be. This is a 6c. All right. I don't want that looking like a b. That might be confusing. But all of the b's are on the left now. So what we're going to do is use greatest common factor to reduce it once again to a single b. So we can take a b out of each of these terms, and we end up with b times cd minus 5 equals 6c. And finally, to get the b by itself, we can just divide by the cd minus 5 on both sides. They cancel out. B is finally by itself on the left, and we see that it's equal to a 6c over cd minus 5. And this is the solution to our literal equation that we're looking for. B is on one side, it's by itself, and there are no b's in the expression on the opposite side. So sometimes these, give yourself plenty of room. These can take up a lot of room to actually work them out. Alright. Example 12, we want to get the h by itself. And so what you can do here is recognize that this is set up as a fraction equal to a fraction. Okay, it is already in proportion form. So what we could do to get this started, and at the same time the h is trapped in the denominator, we want to get it out of the denominator. What we're going to do is just cross multiply. We'll end up with a m times the t minus h, and then a 1 times an a on the right. We distribute, because now the h is in parentheses, and we want to get it out of the parentheses. So we distribute the m, and we get an mt minus an mh equals a. And now h is only in one place, so we simply want to move everything that's not an h away from it, that being the mt and this minus m here. So first thing would be to subtract mt from both sides. That would look like this. mt's cancel on the left. On the right we have an a minus an mt. And at this point the only thing that's attached to the h now is a minus m, and it's multiplying the h. So to get rid of it, we divide. We divide both sides by minus m. It cancels on the left. We have our h by itself, and we also have on the opposite side an expression with no h contained inside of it. So we've isolated our variable and solved our equation. And for our last example, example 13, we have another literal equation in which our LCD ends up being UAM. Alright, In this case, it's different from the previous example. We can't use cross multiplication because we now have 1, 2, 3 fractions instead of just 2 fractions. So no cross multiplying here. But what we do is we take our LCD and we insert it in the numerator of each fraction. So we have a UAM on top of each one, and there's a 1 on the top of each fraction, so it's just 1 times UAM, 1 times UAM, and then another 1 times UAM. And then likewise we can multiply the right hand side of the equation by UAM, but all we have over there is a 0, and so when we do that we still end up with a 0 on the right hand side. Okay, as for the fractions, the denominators cancel, the U, the A, and then the M, and so we end up with a fractionless equation, AM plus UM plus UA. Now we are trying to solve for A, so any term that doesn't have an A gets moved to the opposite side, so that would be this middle term. We subtract UM from each side. We're left with an AM, and a UA equals minus UM. A couple more steps. We have A in 2 places, and so we factor it out. A factored out of these 2 terms on the left leaves us with an M plus U. And to finally finish this problem, we would write the left hand side divided by M plus U, and then the right hand side also divided by M plus U. Okay, so this is the last step, and we have gotten our A isolated to one side, and on the other side we have our solution, and there are no A's over here in this expression, so A is a minus UM over M plus U. So that completes chapter 11. Thanks for watching.